Hello everyone, I'm Heng. Today I'm going to introduce our USENIX security supposing paper about a black box adversary example attack toward FCG-based Android malware detection under incomplete feature information. Android is the most popular mobile operating system, capturing roughly 85% of the global market share. However, due to the open nature of Android, it has become the primary target of mobile malware. The figure below shows the gross number of Android malware from 2013 to 2022. So how to detect Android malware has become a serious security issue in people's daily life. The function call graph provides crucial insights into understanding the workings of Android apps, thus recently attracting growing attention. The FCG-based Android malware detection usually consists of 3 steps. First, the FCG feature is extracted from the Android package file. Second, the FCG is transformed into a feature vector. Third, the feature vector is processed for malware prediction. Existing studies demonstrate that the FCG-based Android malware detection methods can achieve promising performance. Unfortunately, the FCG-based malware detection is vulnerable to adversarial examples, which are generated by imposing well-crafted adversarial perturbation on normal examples. Now, we have an overview on the adversarial examples attack process considered in our work. Suppose an adversary launches a black box adversarial example attack to produce real evasive malware. As shown in left figure, the adversary first gets the DEX file from an APK and further decompiles it into a series of smelly files. The adversary manipulates the smelly code according to its perturbation and rebuilds the code to obtain a new APK file. The adversary then queried the detection system with the generated malware sample, utilizes the received binary decision to update its perturbation, and then rebuilds a new malware sample. In our work, the adversary only knows that the target system uses FCG feature for malware detection. However, the adversary doesn't know the feature granularity and the graph embedding method used by target system. Moreover, the adversary has no information about the architecture, the parameters, and the output probability of the target classifier. We give a detailed explanation about the feature granularity in this slide. In function call graph, a function, when abstracted function, can be used to represent a node. As shown in left figure, a function can be denoted by its function name, class name, package name, or family name. Therefore, there exists 4 feature granularity in function call graphs, which are function level, class level, package level, and family level. Clearly, the knowledge about the feature granularity of the target system is helpful for adversaries to generate adversarial examples. However, the prior knowledge is hard to obtain in practice. Hence, we put forward the incomplete feature information assumption, which assuming that adversaries do not know the feature granularity of the target system. In an adversarial attack, the modification made to the malware APK file gotta meet 4 specific requirements. First, the malware functionality should keep consistently before and after manipulation. Second, malware manipulation should be able to affect the features of all granularity. Third, malware manipulation should be hindered by static analysis inspection. Fourth, manipulation should be non-stationary and cannot be restricted to a fixed set of operations. As a result, we select adding edges in our manipulation method. Let's say we create an edge between 2 nodes by adding a function call between a caller and a callee. Then the rest of problem includes how to create candidate edges and how to select desirable edges from the candidate edges and how to insert the selected edges. First, we introduce how to create the candidate edges. An FCG consists of non-leaf nodes and leaf nodes, as shown in the left figure. The non-leaf nodes are main user-defined functions, and the leaf nodes mainly corresponding to Android standard functions. In our method, user-defined functions are selected as caller, since they are easily inserted with new function calls. Leaf nodes are chosen as calls, since invoking a function that does not invoke others will not trigger unintended calls. Then all the links between callers and calls are candidate edges. The selection of the desirable edges will be introduced later. We first show how to use a new method named try-catch-trap to insert the selected edges. Try-catch-trap first inserts a try-catch block into the caller and places the statement of invoking calling in its trap block. It then adds several statements in front of these function calls. These statements are used to trigger a pre-selected exception. By doing so, try-catch-trap can carefully construct runtime exceptions that are difficult to determine doing static analysis, hence possessing the ability to resist static analysis. Now we answer the question of how to select desirable edges from the candidate edge. Following the architecture of generative adversarial network, our method adopts a generator and a discriminator that are cooperatively trained. The generator is responsible for generating the new edges that need to be added into FCG. It is implemented with an adversarial multi-population co-evolution algorithm. We refer to this algorithm as APOEM. The discriminator is introduced to stimulate the generator to improve its perturbation. It is implemented with a graph convolutional neural network, which acting as a substitute network to simulate the target model. The main change faced by the generator is that the real feature granularity is unknown. To alleviate this problem, we propose APOEM to infer the real feature granularity. It follows the general framework of evolutionary algorithm, but it introduces multi-population to fit the different feature granularity and use cooperation among multiple populations to accelerate convergence. Along with the evolution, the population corresponding to the real feature granularity gradually stand out from the crowd. The attacker only knows the binary decision of its target model, making it hard to currently evaluate individuals. In order to track this challenge, we develop a BCM-based model that simulates the target model and provides evolutionary algorithm with approximate path probabilities. Finally, our method aims to integrate APOEM and substitute model to generate adversarial perturbation. To verify the attack effectiveness, we use our method to attack 32 target models, which including 3 feature extraction models, 3 feature granularity, and 5 classification methods. We use the attack success rate, average perturbation rate, and the interaction round to evaluate the attack performance. The results show that our method achieves an average attack success rate of 99% over 32 target models, hence confirming the effectiveness of our method. When attack family level FCG Android malware detection, as the number of queries increase, the package population and the class population gradually fall to a low level. On the contrary, the survival proportion of the population corresponding to the correct feature granularity gradually increased to a high level. This phenomena conform APOEM convergence to a real feature granularity. We evaluate the performance of our methods on VS_total. To be specific, we use our method to generate adversarial examples through querying the mama droid detector and upload them to VS_total for malware detection. It can be seen that our method can effectively reduce the probability of malware being detected owing to the transferability of adversarial examples. Thanks for your listening.